Hello class, I hope y'all had a great weekend. This video will be going over LE 53 and 54. I find these super interesting, so I hope you did as well. So let's get started. LE 53 goes over radioactive decay. So radioactivity is defined as spontaneous emission of radiation by certain elements. You're going to find out in the notes that this is specific to elements that have an atomic number greater than 83. So it's like PO, I think it's palladium and higher. So these are elements that spontaneously emit radiation, right? And there is 3 particles that they concentrate on. The first one that they look at is the alpha particle. The alpha particle you probably remember from Rutherford. This particle, guys, is massive. It has a lot of mass. It is very big. It has a positive 2 charge. So again, the way that they depict it is with helium. So whenever you see helium, that is your alpha particle. Again, you have a positive 2 charge and it has a mass of 4. The second particle that they go over is your beta particle. The beta particle is tiny, tiny, tiny. It is like minuscule compared to the alpha particle. So the beta particle is your electron. It has no mass and it has a negative 1 charge. So this is your beta particle. Lastly, you go over your gamma particle. Gamma particles have no charge or no mass, but they have high energy radiation. You probably recognize gamma particles if you're like a Marvel fan like myself from the movies. The way that we got the Hulk was because he was exposed to gamma rays. Gamma rays are like, we don't want to be near them. They're not good for us in any way. They can change our genetic makeup. And of course, we don't want that, right? So from gamma radiation, there's 2 different types. You have nuclear radiation. So the keyword is nuclear. It tells you that that is in our nucleus. And then you have electromagnetic radiation. So that is what we get from the stars in the galaxy, like our whole Marvel universe type of thing, right? But those are the 2 different types of gamma radiation. Nuclear radiation, again, that gives you the clue that it is in the nucleus, and electromagnetic radiation, which is from the stars and the galaxy. So which of the particles is the largest? Of course, alpha particles. Think of Rutherford. Think of your protons deflecting because they have a large mass as well. Which are most dangerous? Absolutely gamma rays. Gamma rays, guys, have a very, very short wavelength. They're smaller than the nucleus. They can cause a lot of damage. And what you do need to memorize is that all elements with an atomic number greater than 83, so that's palladium and higher, are radioactive. So again, that means they spontaneously emit radiation. Just spontaneous whenever it happens. So that was our video 1. Our video 2 talks about radioactive decay. This video, watch it again if you need to, if you have any questions. This is what your assignment due date is based on. So again, alpha decay just means that you're using helium as a product. So what you need to remember when you're working out these types of radioactive decay problems is that your reactants must equal your products. So here we have uranium-238. Your products are Th234 and helium. So again, here we have A and B. So my B is 238, that's my mass. My atomic number is 92. So my products must have the same number. So 234 plus 4, because I have 234 and 4 here, gives me 238. That checks out. And then 90 plus 2 equals 92. 238 and 92. So again, my reactants equals my products. I had to plug in an alpha particle. Remember, helium is an alpha particle, so that my reactants equal my products. Now let's look at a beta decay example. So for beta decay, we have an electron as a product. So 234 and 90. And this is our atomic number and our mass. So again, my product is 234. My mass needs to stay the same, but I have 91 as my atomic number. Again, I want it to stay equal. So 234 plus 0 will give me 234. So that equals what I have on my reactant side, right? And 91 minus 1, because this is a beta particle and it means -1 on the electron side, would equal 90. So now it also equals what I originally started with, 234 and 90. So again, the name of the game is making sure that both sides are balanced. Now let's look at our practice question. Here we have 1 and 0, so that means whatever I start with has to have a mass of 1, and 1 minus 1 means it has no atomic number. So if you're thinking of a particle with a mass of 1, this is your neutron. It has no charge, it has a mass of 1, and that's what we're looking at. This is what your question will look like. You're just going to be plugging it in. The best thing to remember is if you have the atomic number, just use your periodic table and put that element there. Radioactive Decay series was that little table that she goes through. Just make sure that you follow the arrows. In the video, I believe it ends with an alpha decay because from palladium to the product, there was a red arrow going down. So again, look at your graph, read the legend, and that should help you out a lot. So again, lesson 53, specifically video 2, will help you with the worksheet if you need to rewatch it. It's not too long. This one, guys, I actually really liked LE54. This explains the difference between nuclear explosion and chemical meltdown. So to start off really quickly, let's define the both. So we have nuclear explosion, which is an uncontrolled chain reaction. The best example would be a bomb. A nuclear explosion is made with the intent to hurt and the intent to not have any control over this reaction. On the other hand, we have a chemical meltdown. So a chemical meltdown occurs in a nuclear plant when there is a fire or an exothermic reaction. So exothermic means there's a lot of energy being produced, right? And this is our nuclear I'm sorry, I'm blanked. This is what happens in a nuclear reaction. There's a lot of energy produced. That's why people are looking at it as an alternative source of energy, because remember, it produces tons and tons more energy compared to our fossil fuels. So nuclear explosion versus nuclear meltdown. The first example is of Chernobyl. So Chernobyl happened in the Ukraine in April of 1986, and this was caused by an operator error. This was a human error, unfortunately. So what happened is the flow of the primary coolant, if you remember, this is mainly the boric acid. Her video is way better. She has the visual and everything. The primary coolant was stopped. They were doing some kind of test or check or something, and they stopped the primary coolant, right? So you have this very, very hot reaction and no primary coolant to keep it cool. Not the best idea, but you know, I'm not a nuclear reactor specialist. So what happened, unfortunately, was that the control rods, remember, you can input the control rods and the fuel rods. If you put the control rods all the way down, they would stop the reaction. But unfortunately, the operator did not do this. The control rods were in there, but they weren't all the way down. So what happens was the reaction continued. The reaction of the nuclear reaction did not stop. So the reaction, which occurs very fast, was very, very hot, and we didn't have that primary coolant or boric acid to help us cool down the reaction. So what happened was that water was turning into steam very quickly, and you can think of like a teapot, I guess, when the steam comes out or whatever, like the top's going to blow off, right? So there was an explosion. The explosion caused a lot of graphite to be in the air. And what you need to know about chemicals, whenever you're dealing with chemicals, sometimes adding water is not the best thing. It might actually make it worse. And unfortunately, that is what happened here. There was a whole bunch of graphite everywhere. People were like, oh my gosh, explosion fire. Like, let's put water on it, right? That was unfortunately a very bad decision, because they put water on it and the hydrogen gas in the air and the graphite, like it was just not a good mix. There was more explosions. So you had your big boom, like boom, and then you had boom, 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 boom. More explosions caused by people trying to treat this with water. Some of these chemical explosions, guys, the fires lasted for 10 days. That's a long time. Again, they can't put it out with water. They just have to let it run its course. There was over 31 deaths, unfortunately, in this accident in Chernobyl. 250 million people in the surrounding areas were exposed to radioactivity. Again, we are not made to be exposed to radioactivity, so this is not necessarily a good thing. This was a chemical meltdown. Again, there was an exothermic reaction, which was due to them not having the primary coolant or boric acid in there. It was not done purposely, like, hey, we want this really uncontrolled reaction. It was unfortunately human error. So the last thing that you have to know about Chernobyl is that it produced a lot of iodine 131. So iodine 131, because that is our mass, that's how we write our isotope, which produces xenon 131. It produced beta particles or electrons, and this is your gamma. Remember, gamma is not that good for us, right? So because we had all that iodine 131, that is a thyroid cancer causing element. So unfortunately, due to this explosion, there's 5,000 children that were diagnosed with thyroid cancer after that. Again, they had nothing directly to do with this accident that occurred, but unfortunately, they had to deal with the repercussions, which is thyroid cancer in children, which is very, very unfortunate. The next one we have is 3 Mile Island. So 3 Mile Island is the only nuclear accident that has happened in the US. It happened in Pennsylvania. That's where it was located in March of 1979. So there was an explosion. What happened here is there was a blockage, guys. Like, unfortunately, you know, we have our secondary where our primary coolant is going. Here we have water. And here you have your pool. So pool is supposed to send water, and here your condenser, right? There is a blockage. So what they had to do is they had to drain the secondary coolant. They had to drain it. They're trying to fix the blockage. While they're trying to fix the blockage, obviously your primary coolant, which is here your boric acid, is going to get very hot. So they had to open up a vent. Again, what they're trying to do is make it cooler, because this is a very strong, very exothermic reaction. So they're trying to vent it, but unfortunately that primary coolant, your boric acid, became too hot. It became too hot. They started losing the coolant, and there was a partial meltdown. So this is why we had an explosion in 3 Mile Island. Again, it was due to the secondary, the blockage of the secondary coolant, which is your water. They had to drain it. They tried to cool it off. They couldn't. It wasn't enough just to vent it, and there was an explosion. Again, it is very unfortunate. I guess the silver lining was that there's no increased probability of cancer for the surrounding people in that area. So according to research, anyone who lived around that area didn't have higher chances of getting cancer. And the last one, guys, Fukushima. I don't know, I really like this lesson for some reason. Fukushima was in 2011 in Japan. What's so unfortunate about Fukushima is that no one did anything wrong. None of the operators had any fault in this. If anything, they were trying to avoid explosions. They were trying their best to fix the situation. But the one that caused it was Mother Nature. So what happened is Fukushima is located on the coast of Japan, so it's right by the water, and they were hit by an 8.8 magnitude earthquake. That is a huge earthquake. We're not used to them here, fortunately, but they had a huge earthquake. The earthquake knocked down the power, but that didn't really affect the plant. They have backup generators. They're prepared, you know. So their 1 through 4 reactors were using their backup generators. They were doing okay. Eventually they'll get energy back. But what really, really hurt them, it'll be part of the answer in your videos as well, was that tsunami. The tsunami that came after the earthquake, because that is what happens when there's an earthquake by the coast. The tsunami soon follows, went over the barriers, and it knocked down the generators. So they had no energy for this nuclear reaction occurring that they couldn't stop. And they couldn't pump coolants. They were trying to vent the system, but again, they had no energy. They had no electricity for the boric acid and the water to be cooling the system. So unfortunately, there was an explosion due to the hydrogen gas. Again, the people working there, guys, it was not their fault. They tried to open the vents. They tried to do everything they could, but the main fault was due to the tsunami knocking down the backup generators. So again, Fukushima is also a chemical meltdown. This was an accident caused by human nature. The backup generators were taken down by the tsunami, and unfortunately, there was so much exothermic energy from the nuclear reaction that there was an explosion. 3 Mile Island was also a chemical meltdown. This was due to the blocking of the secondary coolant, and again, the reaction just got too hot and there was an explosion. So this is lesson 54. Again, for your assignment, it primarily works on the second video from lesson 53 if you need to go back on it. And that's it, guys. I hope you have a great day.